Hello everybody and welcome to NPTEL online certification on semiconductor devices for next generation field effect transistor, a physics perspective, and this is lecture number 44 where we continue with gate-all-around FETs of what we had done earlier in our classes. Now let us look at the various gate-all-around FET structures available with us, right, and this will help you to see what is the meaning of gate-all-around will be absolutely clear to you now. Just look at, say for example, the first one, which is this one. Let us suppose this figure. If you look at this figure here, right, then you see that the gate is surrounding, this is the gate, this is the metal gate, the orange colored, which is the structure here, is surrounding the channel in all the 4 directions, right. It is basically surround gate structure. So, the gate is being surrounded like this. So, if this is the gate material, then you have this as the channel which is through which the electrons are flowing. Now, there are many ways of surrounding the gate. So, one is this one which you see in front of you. Another we have already studied when we were doing FinFETs and Nanowire FETs, where this is the wire which I am talking about, and this side is source and this side is drain, and you have a gate here. And this is a not an insulated gate, but a shorted gate structure. So, whatever potential you give on this gate side, the same potential goes across the whole of the channel. Now, if you look at this is the lateral one where the current is flowing parallel to the surface, right, parallel to the substrate. However, you can also have another type of gate-all-around nanowire FET where the currents are flowing vertical to the surface. So, this is the vertical surface phenomena which you see. So, you see here the currents are flowing in the vertical direction and the gate is in the horizontal plane, whereas in a nanowire gate-all-around, the lateral gate-all-around, the gate is perpendicular to the surface and the channel is along the horizontal plane. Now, so this is another type of FET device where we define these tube as a nanowire device. If you look at the leftmost figure here, there are 2 silicon nanowires, this brown colored here and this brown colored here. These are all simulated structures here, and the gate is surrounding in all the directions once again. This is again a MCB multi-channel we have device where individual sheets of layers form channels. So, there are 3 sheets which form the channel and there is a single gate which forms the channel, right. And on the right hand side, if you see, there is the gate which is surrounding all the channel and all the 4 directions, right. And these are the various different types of gate-all-around FETs which you see in terms of the surrounding the material with all the gates. So, these gates are metal gates here. So, these are all metal gates which you see here, right. Okay. Let us come to the functionality of it and then we will come to the discussion. The functionality is exactly the same as a bulk MOSFET. How? If you take this gate voltage, let us suppose is greater than the threshold voltage of these sheets which you see, these are the sheets here, right. These are the sheets. These are referred to as, maybe let me define them as nanosheets, right. If I define them as nanosheets, then what we get from here is that these nanosheets tends to make these devices very thickness of these devices may be around 8 to 10 nanometers thick they are, right. Though I have shown here that they are triangle or rectangle in nature, here and here they are rectangle, in reality they might be actually rounded in nature, right, and you will have a metal gate here which will be giving the potential. Now, if you give a potential at this particular point, or there will be an inversion layer which will be formed near the edge of the channel, right, just below the oxide layer, and it will be in the 3rd dimension which will be going within the plane of the paper, right, or the plane of your computer. Now, diagrams of the sheets which you see here, right, and interestingly, as you can see, very interestingly, the electron density is maximum at the edges and minimum at the center. Expected also because with increased value of voltage at the edges, you will always have a larger current density at the edges, right? And that's the reasons you see that the whole of it is marked by red colored, where the electron densities are relatively large. Not only that, the electron density is also the highest near the rectangular edge. Which edge? This edge, right? Or even this edge, right? You see these things. So these are dark red colors, whereas this is sort of an orange color which you see, right? And that's true also. Why is it true? Because this is the point where the net electric field, if you find out, is basically given as Ex square plus Ey square root over. So if this is Ex and if this is Ey, then you can appreciate that the value of Ex and Ey will be very large, and therefore the effective value of E. So this can be written as Exy, E as a function of x and y, right? And as you can see, it is orders larger than the intrinsic concentration of the background p type. Now, when the width of the nanowire is somewhere between 30 nanometer and 50 nanometer, there is a volume inversion. What does a volume inversion basically means is that the entire nanowire, inside of the nanowire, has got a larger electron concentration as compared to the edges, right? And since the center don't have any interfaces, for example, if I take this as the channel, the center will have no interfaces, right? Only the electrons which are moving at the periphery here, at this periphery, those are flowing through edges, right? They are flowing through edges, right? And as a result, what will happen is that they will be sustained to large amount of scattering and mobility degradation, and therefore the current will fall down. But if you do a volume inversion, which means that the whole volume becomes now carrier because of heavy concentration of electric field and quantization, the electrons concentration here will exceed large, and as a result there will be no large amount of scattering, and there will be no large amount of mobility degradation, and there will be therefore an enhancement in the current taking place because of very low dimensions of the device. That is what is written here, and that is the reason we write down that the inversion charge density inside the entire nanowire is higher than the background p type doping. So you had initially p type, you want to convert to n type, and that is the problem which you will get. Now if you look at the right hand side figure here, and this is normalized with respect to its own width. Typically if you see, as you move from one edge of the width to other edge, you see the peak happens sometimes very near to one of the edges. You see the peak of the electron concentration or electron density happens at the edges, and the bottom you see there is a decrement in the electron density, right? And in they tend to increase, and that is true also, because even if you look very carefully, when you give an external voltage and when you have a large amount of charge carriers being available at the interface, they tend to screen the electric field, and therefore they sort of not allow electric fields to come inside the channel, and therefore there is a dip in electron density near the center of the channel. Now the last point, if you look, if you lower the width, effective width is basically the total, this total dimension, right, from here to here. If the total width of the device is around 30 nanometer, we see a stronger confinement, and interestingly what happens is that the charge carriers are pushed into the volume, into the inside the volume, right? And that is what is written here, that the inversion layer is pushed 1 to 2 nanometer further away from the surface, and a higher charge inversion density at the center of the nanowire as compared to width of the nanowire when it is 50 nanometers, right? And that is the reason you will have more confinement of the charge carriers. Now let us look at the comparison between a FinFET and a GAA FET, right? So that you know what are the advantages, what are the relative advantages and disadvantages of FinFET and GAA FET. Now if you look at this graph, as you can see here, the effective width of a FinFET is W fin plus 2 H fin. W fin is this one, plus 2 H fin is this, plus this, right. And if you look at nanowire sheet FET, it is W fin which is available because this is common to all of them, and plus 2 n times H fin plus Hs. H fin is what? W fin is this one, is W fin, and plus Hs is this one, right, and 2 n times. So, what you will get is basically W fin plus 2 n W fin. Why 2 n W fin? Because there are, suppose there are n sheets available, one fin here, another fin here. So, I get 2 n. So, I get 2 times W fin for each case, and I get 2 times Hs for each of the nanosheets. And as a result, what you will get is that you will get 2 n times Hs which you will get. So, effectively what you, the total width, because see, I will explain to you, try to explain to you much more easily. Suppose this is one sheet, this is another sheet, this is another sheet. So, there are n is equals to 3. So, n equals to 3 in our case. Now, this is my W fin. So, each sheet has one W fin here, one W fin here. So, each sheet has therefore 2 W fins. So, if there are n sheets, there will be 2 n times W fin which will be available to us. And since Hs is 1, this one is Hs, and there are 2 Hs per fin, therefore 2 n time Hs happens to be the total width. So, if you add these two, I get the total surrounding width available to us, and an extra W fin will be added to it. Extra W fin is added, width of the fin, and that is the reason you get this into consideration. Similarly, if you take a nanowire FET where the channels are sort of round or elliptical in nature, then I get W effective NW is equal to W fin plus n pi into W fin, right, where W fin is given by the sort of a diameter of that whole area. Now, if you compare on the right hand side, you see the green colored one data is for the FinFET, dashed blue lines are basically nanosheet FETs, right. So, obviously, as you can see, nanosheet FETs have, for the same amount of gate voltage, has got a larger current, you see. So, you see that this is around 52, 53, 50 microamp, whereas for FinFET it is around 30 microamp. So, there is automatically a 20 to 25 microamp increase in the current in saturation in nanosheet FETs, in GAA FETs as compared to a FinFET. Assuming that the area, the footprint area is remaining the same, you are also assuming that the fin height to be same for both the cases, and you are also assuming that the nanosheet height is also same for all the cases, Hs, right, is same for all the cases, which is distance between this point and this point. This is the sheet pitch. In FinFET, if you remember fin pitch, this is analogous to that, where how far the two channels are separated from with respect to each other. Now, let us come to the FinFET width folding ratio. As I discussed with you, the current flowing through the device is not only flowing through the top wall, but it is also flowing through the two vertical side walls of the fin. So, if you look carefully here, right, and if I rub, let me say, just let me erase it, and let us look at this particular point here, right. So, this is the side wall and this is the top wall. So, the electrons are not only flowing through this top wall, but they are also flowing through these side walls. And please note that the way the top and side walls are made ensures, not ensures, but in reality what happens is that when you do a fabrication, the number of lattice points are different for top wall and side wall, and therefore, the mobilities are different because the scattering is different. Now, the effective channel width, as I told you, is W fin plus 2 H fin. Now, the width of the mask layout or the footprint equals to the fin width, and the effective sizing of the folding ratio the channel can characterize as W fin by W fin effective, which is W fin by W fin plus 2 H fin. So, you see W fin is the width of the FinFET, keeping in mind the structural issue, and H fin is being added because of the height of the fin. So, we define folding ratio as the width of the fin divided by the total width. So, width of the fin divided by the total width is given as the folding ratio. If you have a lower folding ratio, this implies that you will have a higher chip density, and therefore you can move into a higher advanced technology where your layouts are very stringent and very curtailed down. So, if we need to sustain a lower folding ratio for more compact definition here. Now, for a GAA structure, the vertical nanosheet FET VNS FET is considered to be the most scalable structure for MOS device till now, right. We do have Fox sheets and CFETs coming into picture. We will not go into details of that at this early stage, but we are sure that for a GAA structure, the VNS FET has been considered to be the ultimate scalable structure. If the sheet height is given as HS, right, H of S, then the effective channel width of the sheet will be given by 2 times WS plus HS, correct. And if there are n such sheets available, I get the total this to be this much, and therefore we write down that the spacing between the sheet is HS, the achievable total H depth or fin height produced by certain HN process H fin, then the total nanosheets, total number of nanosheet n is given by H fin upon HS 1 plus alpha. You can in fact remove this one even, then it is basically H fin by HS. Why? What is HS? You just look carefully here. HS is this one, and what is H fin? H fin as per our understanding is this one. So, if you divide this by this, you get the total number of sheets up, except that you also have this constant here, you can remove this. So, that part is coming from 1 plus alpha. So, 1 plus alpha takes care of the fact as the distance between. So, if the distance between the two sheets would have been 0, then effective value of n would be H fin, capital H fin by small hs, whereas if you have an alpha coming into picture which segregates how many distance between the two fin in terms of pitch, then it is H fin by Hs plus 1 plus alpha. So, if your alpha value is large enough, you will have a reduced number of n or number of nanosheets with you. Now, obviously as you can appreciate, n should be an integral value, it cannot be 1.5 or 2.5, it could be either 3 or 4 or 5 and so on and so forth. So, the effective width of the nanosheet is given by therefore W fin plus this whole quantity which you see in here, right. This is basically equivalent to 2 n times W fin plus Hs, and by some manipulation I get 2 H fin by 1 plus alpha 1 plus W fin by H fin. Now, quite interestingly, if you look very carefully, if the width of the fin, which is this one, width of the fin, this one, and height of the fin is this one, if you look at these two objects, if they are exactly equal, which means that it is a perfectly square sheet which you are using, then this will be effectively equals to 1, you will get 2 and you will get W fin times plus 4 times H fin divided by 1 plus alpha, that will be your WNS effective, right. Whereas, if it is highly rectangular in nature, then Hs will be very small as compared to W fin, right, and therefore this quantity will be relatively larger, W effective NS will be also large, that is expected. Therefore, having a highly rectangular shape will lead you to a larger value of effective nanosheet thickness. Now, large spacing results in large portion of the vertical sidewall not being used as conductance channels, which means that if your spacings are large between two nanosheets, then you might not actually use the sidewall. So, rather than a GAA device, it will be only the electrons will be flowing across only two sides of the channel, right. So, in order to have a larger effective width of a FinFET with respect to the same width and total height, we define this as the inequality which one has to sustain in order to achieve a larger effective width than a FinFET. So, if you have a FinFET and a nanosheet FET, you need to ensure that for FinFET and nanosheet FET, this inequality holds good, the last inequality. If it holds good, that will give you a relatively higher sort of advantage for NS sheet FET. Alpha is relatively smaller than W fin by H fin, and the nanosheet structure should have a better folding factor if the spacing between the nanosheet is smaller than the fin width. And that is a sort of a rule of thumb that try to keep this difference between the two structures smaller than the nanosheet width itself. And of course, as I discussed with you earlier during dielectric also, that the minimum spacing is primarily limited by the material property and the fabrication process, right. If the material is not very reliable, you might have a leakage taking place. So those things will finally determine the final minimum spacing between the two nanosheet. The effective width for a single nanosheet nanowire FET is given by pi times W fin, and where the cross section is not round, the width can be smaller than pi times W fin. If there are n nanowires with the bottom flat channel, then the total width is given by W fin into n times W fin, right. And if you consider the spacing between the nanowires is alpha times W fin, the fin height produced by the process is h fin, then the total number of nanowires will be given by this. Already I have discussed with you this point, where n is an integer. Now, if you again the same concept as in previously, if you want that you have a better folding ratio than FinFET, then you need to maintain this inequality in a much more detailed manner. Once you maintain this inequality, you ensure that your folding factor or folding ratio is much better. So, to conclude this whole discussion, typically alpha is chosen to be around 0.57, right. Similarly, therefore ensures that the spacing between the nanowires should be less than 57% than about of the nanowire size. So, you take the nanometer size diameter, and your nanowire spacing between the nanowire should be less than 50% of the nanowire's thickness. Now, if you make alpha very large, say 1.67, the nanosheet structure is better than FinFET only when the fin width is larger than 10 nanometer. So, these are some of the design criteria which people have found out over a period of time. I have taken it from this research paper. You can actually go through these research papers to get it. And as you can see, on the left hand side the folding ratio, on the right hand side also folding ratio, 0.67 being the most lowest one, or when you make alpha larger and larger, the folding factor also starts to increase. So, this is for different various values of nanosheets, right. Similarly, if you look at the left hand side, as you increase the value of alpha, the folding ratio also increases for larger amount of nanosheet wire. So, what we have concluded from all these discussions till now is that we have been able to formulate at least one basic policy for a nanosheet FET. What should be the design criteria that it performs better than FinFET for the same amount of layout area or the same amount of silicon area. So, to conclude this discussion, let me conclude what we have done till now. We have shown you the various types of GAA FET, right. So, we have shown you various types of gate all around FETs, right. We have looked into the various design criteria for GAA FETs, and then we thought of giving you a basic idea of optimization of GAA FET optimization, which will help you to improve the device characteristics for the same amount of silicon area. Now, open-ended question to all of you is, out of FinFET and GAA FETs, what criteria would you choose? For example, do you want a higher on current, or do you want a better transient response? I would recommend that go through research papers, go through textbooks, and you will find answers to these questions. So, one device does not give you all the advantageous features, right. So, you need to have for example, the nanosheet structure available with you and optimize the nanosheet structure for a best performance design. It can be better than FinFET as well, right. However, I will show you in the next turn that its fabrication is relatively a difficult process as compared to a single FinFET or even a bulk MOSFET. Thank you.